So students, you saw in the video that the paper and the stone fell to the ground at the same time. Now we will derive the equation for acceleration due to gravity, small g. According to Newton's second law of motion, it says that force acting on a body results in its acceleration. Hence, the gravitational force acting on a body will result in its acceleration, which is called acceleration due to gravity, denoted by small g. To derive acceleration due to gravity, g, we use the Newton's law of gravitation. Let's consider an object released from a height on the surface of the earth. According to Newton's universal law, force acting on the object is given as F is equal to G capital M into small m upon r square, where G is the universal constant of gravitation, capital M is mass of earth, and small m is mass of the falling object. As the force of gravity, the object gets accelerated, and acceleration is given by A is equal to F upon m. This is the force equation which you studied in standard 9th. Acceleration due to gravity will replace A, and hence G is equal to F upon m. Substituting gravitational force F in the above equation, we get G is equal to G, capital G into M into small m upon r square divided by small m. Therefore, G is equal to capital G into capital M into small m upon r square into 1 upon small m. Cancelling the common term small m, we get G is equal to Gm upon r square. The equation thus tells us clearly that mass of the falling object will not affect acceleration of it. As seen in the video, the stone and paper will fall at the same rate and reach the ground at the same time. Derivation of value of G. We have derived small g is equal to capital G into m upon r square. Now let's put the values of capital G, 6.67 into 10 raised to minus 11. Capital M is equal to mass of the earth, 6 into 10 raised to 24. And R is equal to radius of the earth, 6.4 into 10 raised to 6 the whole square. After putting the values in the equation, we get G is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 the whole square. Therefore, the value of acceleration due to gravity, small g, is equal to 9.77 meter per second square. Now, students, it's quiz time. Observe, think, and answer. Who is right? Two important scientists came up with different ideas about how fast objects fall towards the earth. Your job is to plan an experiment to find out who was right. Aristotle in 50 BC stated the heavier the object is, the faster it will fall to the ground. Galileo in 1525 AD stated objects of different mass that are dropped from the same height will reach the ground at the same time. So students, who is right? Correct. Galileo had proved it experimentally years before Newton, and Newton mathematically proved Galileo right. And that's the beauty about gravity. Now we see variation in the value of small g. Value of g remains same, that is 9.8 meter per second square, for all falling bodies on the surface of Earth. But it can vary due to the following. Along the surface of Earth, we all know Earth is not a perfect sphere, it is bulging at equator. See over here, it's bulging at the equator and flattened at the poles. Flattened at the poles. Hence, radius is smallest at poles. Hence, the value of g calculated will be 9.832 meter per second square. At the equator, the radius will be largest. Hence, value of small g calculated will be 9.78 meter per second square. Students, you have seen the values. Now there is a question for you. Tom lives in Kenya. Ken lives in Iceland. And both of them have a fall. Can you tell what will be their rate of falling? Tom and Ken. Think. Yes? Hint. Iceland is at the poles. Kenya is at the equator. So, Tom, what will be the rate? He's in Kenya, so 9.78 meter per second square. And what about Ken, who is at Iceland? 9.832 meter per second square. I hope you got it right. Now the second change in the value of g is because of the height. As we go above the surface of the earth, value of g decreases. So if an object falls at a small height from the surface, value of g will remain 9.8 meter per second square. If it falls from Mount Everest, whose height is 8.8 kilometer, the value of g remains 9.8 meter per second square. Because compared to the radius, this height is negligible. But from a communication satellite, which is about 35,700 kilometers from the surface of Earth, value of g will be 0.225 meter per second square. So students, you have seen the value of g on Mount Everest, seen the value of g from a communication satellite. Now, there's a question. Whose acceleration will be more? The man falling from mountain or man falling from satellite? Yes? Correct. The man falling from mountain will be more as the value of g is more. And the man falling from the satellite will be lesser. Now how much? You have to take the difference and you will get the answer. We move to the next variation. Depth. Value of g goes on decreasing with the depth because value of r goes on decreasing and part of the earth that contributes towards gravitational force felt by the object also decreases. That means value of mass will decrease. Hence, combined change in value of R and M. Now, we all say, what is your weight? We also ask, what is the mass? But students, do you know both the quantities are not one and the same? Many times when we ask questions, what is your weight? You say you weigh 50, 60. But actually in physics, weight of an object is the force with which the earth attracts the object. The weight of the object is equal to mass of the object into acceleration of gravity. So mathematically, W is equal to mg. That is mass of object into acceleration due to gravity. If you remember, when you went on field trip to Nehru Science Center and Planetarium, you must have weighed at the planetarium where there were different weigh machines, one of Earth, Moon, Sun, and maybe Jupiter. And what did you observe? That everywhere your weight was changing. So what does that say? The mass doesn't change, but the weight changes. Why? Because weight depends on the value G. So wherever the value of G is lesser, there the weight will be lesser. And that is why you know when we go on moon, we are not able to walk. To know more, please watch the following video.